Hi everyone, we're on the last question now of this paper, and we've got a kind of implicit differentiation kind of question, and I'd say this is an extremely challenging question. It's not that it's particularly crazily conceptually difficult, but it's just there's lots of places where you could make little arithmetic slips with signs and so on. So let's have a look at the first bit. So it says the curve C has the equation x add y cubed is equal to 3x squared minus 3y minus 2. Find an expression for dy by dx in terms of x and y. So we're going to basically expand and then differentiate. So expanding, first of all, x add y all cubed. Now in order to expand that, what I've done is I'm using the binomial expansion. Okay, just a quick way of expanding x add y cubed. So you think to yourself, you've got x cubed, and then the binomial coefficient is going to be 3x squared y, add 3xy squared, add y cubed. So just a really quick way if you have to expand a cubic, rather than sort of like thinking about it longhand, just to kind of use the binomial expansion. And then we've got 3x squared minus 3y minus 2. That's the right hand side. Okay, so we've now got to differentiate 3x squared y. That's going to be the product rule, and we've got to differentiate 3xy squared, also going to be the product rule. So in these two little thought bubbles, I've done the product rule here. So I've said that my u is equal to 3x squared, my v is equal to y. So therefore my u dashed is 6x, and my v dashed is going to be dy by dx, because we're differentiating implicitly. So my product rule, which I always remember backwards for some reason, but u dash v add u v dashed, but it doesn't matter that I remember it back to front because it's an add. So it's still okay. So u dash v is going to be u dashed times v, so 6xy, plus u v dashed. U is going to be 3x squared, and v dashed is dy by dx. So we end up with 3x squared dy by dx. Over here now, let's turn our attention to 3xy squared. So u is equal to 3x, so u dashed is 3. V is equal to y squared, so v dashed is 2y dy by dx. Subbing into the formula u dash v add u v dashed, we have that u dashed is equal to 3 times by v, which is y squared, so 3y squared, and u, which is 3x, times by v dash, which is 2y dy by dx. So those results now can be put in, okay? So let's have a look at these two results. So one there, and those results there, okay? So we had our 3x, when we differentiated it, our x cubed became 3x squared, so that's at the start. This here is that our derivative of that bit. These terms here, those two there, they're the derivative of the 3xy squared. So now we've just got to differentiate y cubed. Okay, so we go underneath that bubble, pop out there. That goes to 3y squared dy by dx. And then 3x squared differentiates into 6x, and then minus 3y goes to minus 3 dy by dx, and the 2 disappears. So we've got a rather long and cumbersome looking expression here. Wow, there's a lot going on there. Just look at all that. So we've got to try and somehow make this whole thing say dy by dx is equal to something. Now usually when they've done this kind of thing in the past, they've given you a point so you can sub it in and boil the whole thing down to be something a lot simpler, but they haven't here. So it's the last question, so we've just got to do the whole thing algebraically. So it's a lot of terms and it looks quite complicated, but all we need to do is just gather together all of our dy by dx terms over to one side of the equation. So we're going to take that one, we're going to take that one, we're going to take that one, and we're going to take that one, and bring them all over to the left. Everything else is going on the right hand side. So the 6x is going on the right hand side, there it is. The 6xy is going over to the left hand side, there's minus 6xy. The 3x squared is going to go over to the left hand side, so minus 3x squared. And the 3y squared is going over to the right hand side as well, so 3y squared. So all of those are being brought across to the right hand side. So now we factorize out our dy by dx from everything that we've got, and we've got this, that's what we get, and there's our right hand side. Then we divide. So we get, this is the expression that we've got so far. So what can we do? We need to see if we can tidy this up. Well, the first thing that springs to mind is there's a common factor of 3 in every single one of those terms. So let's have a look at that. So we can divide our whole expression by 3. Okay, so every single term is getting divided by 3. So divide by 3, divide by 3, divide by 3, divide by 3. So we get this, 2x minus x squared minus y minus 2xy plus x squared plus 2xy plus y squared plus 1. Now you could leave it like that. That would be okay. I don't think you would lose a mark there because they haven't said anything about factorising it fully. But just for interest, it does look as though this could factorise, because if you take a minus outside of this first bit here, you've got x squared add 2xy add y squared, which factorises into x add y all squared. So that's kind of neat. And here you've got x squared add xy add y squared, which factorises into x add y all squared. So x add y all squared. So you can, if you want to be, tidy it up as much as possible, it could further simplify by factorising into this expression there. But as I say, this one is also okay. So quite intense algebra there. So quite a lot of terms, easy to drop a sign. But that was 5 marks. So I think, a difficult but fair 5 marks there. Part B, what's going on here? It says the point 1, 0 lies on C. Show that the normal to C at P has that equation. So pretty straightforward. Now we're just going to sub in our point 1, 0 into our dy by dx to find out the gradient at that point. Okay, so there's our curve and here's our tangent, and we're trying to find the equation of the normal. Yeah. So there's our equation of our normal. So we find out our dy by dx when we sub in 1 and 0 is a half. So therefore the gradient of the normal is going to be -2. So if that's a half, that is -2, because remember that m1, m2 equals -1. So we've got our gradient of our normal. We sub in the point P, 1, 0. Using y minus y1, we're going to get the equation of the normal. And it turns out to be y is equal to -2x add 2 as required. So that's super nice. So we know we're on track with that. Now, part C, the very last part of the paper, I believe. Let's have a look. Oops, giving us a lot of pages for working. My goodness, they're giving us a lot of pages for working there. But yes, the very last part, the very last question. So we can expect this to be tricky. It says prove that the normal does not intersect, does not meet C again. You should use algebra for your proof and make your reasoning clear, and it's worth 5 marks. So let's have a look and see what we've got. So here's our tangent to our curve, and we've got our normal like this. Okay, so there's our normal, which we've established has the equation y is equal to -2x add 2. Now we don't know what this curve looks like. I've just drawn some sort of generic squiggle there. Obviously that's not a scientific thing. But what we've got to try and prove is that this line only intersects this curve C at just that one point P. So normally, let's think, what do we normally do? Surely it's got to have something to do with a discriminant somewhere along the line. And my first instinct is if we sub in the y equation into the curve, maybe it will boil down into some kind of equation from which we can deduce the fact that there must only be one point of intersection. So we're going to sub in the y is equal to -2x add 2 into our equation and see what that gets us and see whether we can deduce anything from that. So that's our first step. So here we go. We're subbing in -2x add 2 into the original equation. Now, x minus 2x is -x, and we've got +2 there. So when we expand -x add 2 cubed, again using the binomial, it's going to go to -x cubed plus 3 times -x squared plus 2 to the 1 plus 3 times -x to the 1 plus 2 squared plus 2 cubed. So really nice straightforward way to expand that. 3x squared is there. This goes to plus 6x, and a minus times a plus makes -6, and then we've got -2. So we can now gather, we can basically work out what all of these are. We've got -x cubed here. We have got, what have we got for this next one? we've got a minus x all squared is going to be x squared, 3 times 2, so plus 6x squared. Minus x times by 3 times by 2 squared is going to be 3 times 4, so it's going to be minus 12x. 2 cubed is 8. And then those terms, the only thing we've done there is minus 6 minus 2 is minus 8. So let's take the whole thing over to one side, giving us x cubed minus 3x squared, because we get, what do we get? Where's our minus 3x squared come from? Oh yes, so we're taking that over to that other side, and then we've got 3x squared, take away 6x squared is going to be minus 3x squared, and then add that 12x over onto the 6x, gives us 18x, and then we're going to have minus 8 minus another 8 is minus 16. So that's our cubic equation. Now, this equation, remember, has been formed by subbing in the equation of the normal into the parametric curve. And we know that there is a solution when x equals 1, okay, because we know that the point P is our point of intersection. So basically, when x equals 1 is a solution to this equation that we've just got. So if x equals 1 is a solution, then that means that x minus 1 is a factor. So I'm going to do my algebraic long division to divide my cubic, and then we'll see what kind of a quadratic we get. So here's our cubic that we've just deduced, and we're going to divide it by x minus 1, which we know is our factor. So I like to do my long division in this way. I basically compare my x with x cubed. I say, what do I need to do to my x to turn it into x cubed? I times by x squared. So you times that by x squared, giving you x cubed minus 2x squared. Take them away from each other. Minus 3 minus minus 1 is minus 2. Drop that down, repeat the process. What do I need to do to x to change it into minus 2x squared? Times by minus 2x. So I times this by minus 2x, giving me minus 2x squared plus 2x. Subtract them, that's 0. 18 take away 2 is 16. Drop the 16 down and repeat the process. I look at my x, I say, what do I need to do to change it into 16x? Times it by 16. So you times this by 16, write it down there and take it away, and it happens to go in with no remainder, which is super encouraging. So therefore, the polynomial, cubic polynomial that I formed earlier in the question can now be written like this. So this is great, because if we can show that this discriminant, if we can show that this b squared minus 4ac is less than 0, then that means there's going to be no further solutions to the equation that we found by subbing in the equation of the line into the curve, which would mean that there is only one point of intersection. So all we need to do now is just evaluate our discriminant, and if it's less than 0, we've shown that there is only one point of intersection. So our b is minus 2, so that's going to go to minus 2 squared is going to be 4. Minus 4 times a, which is 1, times c, which is 16. So 4 minus 64 is minus 60. Minus 60 is less than 0, so therefore there are no solutions coming from this quadratic. So therefore x equals 1 is the only solution, and therefore the tangent, no, it's not the tangent, it's the normal. So therefore the normal only intersects the curve once, as required. So yeah, quite challenging that, but as I say, the kind of, I think challenging but fair is the way I would describe question 15. So I hope that you found that helpful, and that concludes this particular paper, and I'll see you in the next video.